Hello, and welcome to Mind Whisper channel. Tonight, we're embarking on a journey that spans from the deepest trenches of our oceans to the farthest reaches of the observable universe. We'll explore the remarkable story of our planet Earth, from its violent birth to its current status as the only known world harboring life. We'll discover how ancient microbes transformed our atmosphere, making it breathable for complex life. We'll venture into the crushing depths of the ocean floor and soar through space to witness the birth and death of stars. As you settle in, let your mind wander through these cosmic and terrestrial wonders. Some facts will fill you with awe at the sheer scale of our universe. Others will reveal the intricate processes that make our small blue world so special. Whether you're drifting off to sleep or simply relaxing, allow these stories of science and discovery to wash over you. If you enjoy this journey and would like to explore more wonders with us, please consider liking and subscribing below. But for now, all you need to do is breathe deeply, relax, and let's begin our exploration of space and Earth. 4.5 billion years ago, in a quiet corner of the Milky Way galaxy, something remarkable began to happen. A massive cloud of gas and dust, remnants from exploded stars that had died long before, started to collapse under its own gravity. This wasn't a sudden event, but rather a slow, inevitable gathering of material that would eventually become our solar system. Within this swirling disk of cosmic debris, clumps of matter began to stick together, growing larger through countless collisions over millions of years. Among these growing bodies was a young world that would one day be called Earth. In its earliest days, our planet was nothing like the oasis of life we know today. It was a hellish realm of molten rock, bombarded constantly by asteroids and comets that slammed into its surface with devastating force. Each impact added more material to the growing planet while also generating tremendous heat. The surface was an ocean of magma, glowing red and orange, with temperatures reaching thousands of degrees. There was no solid ground, no water, no atmosphere capable of supporting life. During this violent period, something extraordinary happened that would shape Earth's future in profound ways. A Mars-sized body, sometimes called Theia by scientists, collided with the young Earth in an impact of unimaginable violence. The collision was so massive that it liquefied both bodies, sending enormous amounts of debris spiraling into orbit around what remained of Earth. Over time, this ring of debris coalesced to form our moon, which even today bears the scars of its violent birth in the form of countless craters. This impact had another crucial effect as well. It tilted Earth's axis to its current angle of about 23.5 degrees, giving our planet its seasons and helping to create the stable climate zones that would later prove essential for life. As millions of years passed, the bombardment gradually subsided. The young Earth began to cool, and its surface started to solidify into a thin crust of rock. But beneath this fragile shell, the planet's interior remained intensely hot, with temperatures at the core reaching over 9,000 degrees Fahrenheit, hotter than the surface of the sun. This internal heat came from three main sources: the leftover energy from Earth's formation, the decay of radioactive elements deep within the planet, and the heat generated by the immense pressure of all the material pressing down toward the center. The cooling Earth began to differentiate, meaning its materials separated by density. The heaviest elements, primarily iron and nickel, sank toward the center to form the core. Lighter materials rose toward the surface, eventually forming the mantle and crust. This process created the layered structure we observe today, a solid inner core of crystallized iron, surrounded by a liquid outer core, where swirling currents of molten metal generate Earth's magnetic field. Above this lies the thick mantle of semi-solid rock, which flows very slowly over geological timescales, and finally the thin crust upon which all life resides. Earth's magnetic field, generated by those churning currents in the outer core, proved to be one of the planet's most important features. This invisible shield deflects most of the dangerous charged particles streaming from the sun, known as the solar wind. Without this protection, these particles would gradually strip away our atmosphere, much as they did on Mars after that planet's magnetic field weakened and eventually disappeared. The magnetic field also gives us the aurora borealis and aurora australis, those shimmering curtains of light near the poles, where some solar particles do manage to interact with our upper atmosphere. As the crust continued to cool and thicken, volcanic activity remained intense. Countless volcanoes erupted across the surface, spewing not just lava, but also gases that had been trapped in the planet's interior. These volcanic outgassings gradually built up Earth's first substantial atmosphere, composed primarily of water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, and other gases. Notably absent from this early atmosphere was free oxygen, the gas that would later become essential for complex life, but which at this time was virtually non-existent. The water vapor in the atmosphere eventually reached a critical threshold. As the planet cooled further, this vapor began to condense into clouds, and the first rains fell. But these weren't gentle showers. They were torrential deluges that may have lasted for thousands or even millions of years. The rain filled the lowest areas of Earth's surface, creating the first oceans. These early seas were hot and acidic, very different from today's oceans, but they provided the environment where life would eventually emerge. For much of human history, people assumed the continents were fixed in place, permanent features of Earth's geography. But in the early 20th century, a German meteorologist named Alfred Wegener proposed a revolutionary idea. The continents had once been joined together in a single supercontinent, which he called Pangaea, and had since drifted apart to their current positions. He based this hypothesis on several lines of evidence, including the remarkable fit between the coastlines of South America and Africa, as if they were pieces of a jigsaw puzzle that had been pulled apart. Wegener also noted that identical fossil species appeared on continents now separated by vast oceans, and that mountain ranges and rock layers seemed to match up across these divides. Despite this compelling evidence, most geologists of his time rejected the idea. The main objection was simple. Wegener couldn't explain what force could possibly be strong enough to move entire continents across the Earth's surface. Without a mechanism, continental drift remained controversial and largely dismissed. The breakthrough came in the 1950s and 60s, when scientists began systematically mapping the ocean floor for the first time. What they discovered revolutionized geology. Running down the center of the Atlantic Ocean and through all the other major ocean basins were enormous underwater mountain ranges called mid-ocean ridges. These ridges marked places where new oceanic crust was being created as magma rose from deep within the Earth and solidified. But the real revelation came when researchers studied the magnetic properties of rocks on the ocean floor. When lava erupts and cools, magnetic minerals within it become aligned with Earth's magnetic field, essentially recording the direction of the magnetic poles at that moment in time. Scientists knew that Earth's magnetic field has reversed many times throughout history, with the north and south magnetic poles switching places. These reversals occur irregularly, sometimes remaining stable for hundreds of thousands of years before flipping in a process that may take only a few thousand years. When researchers mapped the magnetic orientations of seafloor rocks, they found something astonishing. Parallel stripes of alternating magnetic polarity on either side of the mid-ocean ridges, perfectly symmetrical like a barcode. This pattern could only be explained one way. New crust was continuously forming at the ridges and spreading outward in both directions, recording each magnetic reversal as it went. This process, called seafloor spreading, provided the mechanism that Wegener had been missing. But if new crust was constantly being created at mid-ocean ridges, something had to happen to the old crust, or else Earth would be expanding like a balloon. Scientists found the answer in deep ocean trenches, the deepest places on Earth's surface. At these trenches, old, cold oceanic crust was plunging back down into the mantle in a process called subduction. As the dense oceanic plate descended, it would melt and eventually be recycled, completing the cycle. This understanding gave birth to the theory of plate tectonics, which explains that Earth's outer shell is divided into several large plates of rigid rock that float atop the semi-molten mantle below. These plates are constantly moving, driven by convection currents in the mantle, where hot material rises toward the surface, cools, and sinks back down in a slow but powerful circulation. The plates typically move at rates of just a few centimeters per year, about as fast as fingernails grow, but over millions of years, this imperceptible motion reshapes the entire surface of our planet. Where plates pull apart, as at mid-ocean ridges, new crust forms and oceans widen. Where plates collide, the consequences depend on what types of crust meet. When two oceanic plates converge, the older, denser plate subducts beneath the younger one, creating deep trenches and chains of volcanic islands. When an oceanic plate meets a continental plate, the oceanic plate slides beneath the lighter continental crust, producing volcanoes on land like those in the Andes Mountains or the Cascade Range. When two continental plates collide, neither can easily subduct because both are too light. So instead, the crust crumples and pushes upward, creating massive mountain ranges like the Himalayas, which are still rising today as India continues pushing into Asia. There are also places where plates slide past each other horizontally, called transform boundaries. California's San Andreas Fault is a famous example, where the Pacific plate grinds past the North American plate, occasionally sticking and then releasing in sudden jerks that we experience as earthquakes. Indeed, the vast majority of earthquakes and volcanoes occur along plate boundaries, making these zones both geologically active and potentially dangerous for human populations. The theory of plate tectonics explains so many previously puzzling observations that it quickly became the unifying framework for understanding Earth's geology. It explains why earthquakes and volcanoes occur where they do, how mountain ranges form, why certain rock types and fossils appear where they're found, and how the continents have wandered across the globe throughout Earth's history. Looking at the patterns of ancient magnetism preserved in rocks on different continents, scientists have been able to reconstruct the positions of the continents throughout hundreds of millions of years, watching in their mind's eye as supercontinents assembled and broke apart in a slow dance that continues today. For the first half of Earth's existence, our planet's atmosphere was fundamentally different from the one we breathe today. While nitrogen was abundant, as it still is, the atmosphere contained virtually no free oxygen. Instead, gases like methane, carbon dioxide, and hydrogen sulfide dominated, creating an environment that would be immediately lethal to humans and most modern life forms. This oxygen-poor atmosphere persisted for over 2 billion years, nearly half of Earth's current age. The transformation of Earth's atmosphere from toxic to breathable represents one of the most profound changes in our planet's history, and remarkably, it was brought about by some of the smallest organisms on Earth, cyanobacteria. These microscopic single-celled organisms evolved perhaps 3.5 billion years ago, but they possessed a revolutionary capability that would eventually reshape the entire planet. They could perform photosynthesis, using energy from sunlight to convert carbon dioxide and water into sugars for food, with oxygen as a waste product. At first, the oxygen produced by these early photosynthesizers didn't accumulate in the atmosphere. Earth's surface and oceans were full of chemicals that readily reacted with oxygen, essentially soaking it up as fast as it was produced. Dissolved iron in the oceans was particularly effective at consuming oxygen, combining with it to form iron oxide compounds that precipitated out and sank to the ocean floor. These reactions created the banded iron formations we find in ancient rocks today, layers of iron-rich minerals alternating with other sediments, representing billions of years of oxygen production being locked away in stone rather than escaping to the atmosphere. Volcanic gases also consumed oxygen quickly. Hydrogen sulfide and hydrogen from volcanic eruptions would react with any oxygen present, preventing it from accumulating. The early Earth was a reducing environment, meaning it was rich in substances ready to grab oxygen atoms and bind them into compounds. For cyanobacteria, oxygen was merely an unwanted byproduct of their metabolism, something they had to get rid of to survive. But gradually, over hundreds of millions of years, the oxygen-hungry materials at Earth's surface became saturated. The iron dissolved in the oceans was used up, forming the last of the great banded iron formations around 2.5 billion years ago. Volcanic outgassing continued, but there weren't enough reducing gases to keep up with the steadily increasing oxygen production from the expanding populations of cyanobacteria. Finally, around 2.4 to 2.3 billion years ago, oxygen began to accumulate significantly in the atmosphere for the first time. This event, known as the Great Oxygenation Event, happened remarkably quickly on geological timescales, with oxygen levels rising from near zero to perhaps 10% of present levels in just 1 to 10 million years. While that might seem slow by human standards, it represents an eye blink in Earth's 4.5 billion year history. The consequences of this oxygen catastrophe, as some scientists call it, were profound and far-reaching. For organisms that had evolved in an oxygen-free world, free oxygen was highly toxic. Oxygen is a reactive molecule that can damage cellular components through oxidation, and many of the ancient microbes had no defenses against it. The Great Oxygenation Event may have caused one of the first great mass extinctions in Earth's history, as countless species adapted to the old atmosphere were poisoned by the new oxygen-rich environment. The rise of oxygen also dramatically affected Earth's climate. Methane is a potent greenhouse gas, trapping heat far more effectively than carbon dioxide. In the oxygen-free early atmosphere, methane was abundant and helped keep Earth warm, despite the sun being about 30% dimmer than it is today. But oxygen reacts with methane, breaking it down into carbon dioxide and water. As oxygen levels rose, methane levels plummeted, and Earth's temperature dropped sharply. This may have triggered one of the most severe ice ages in Earth's history, the Huronian glaciation, when ice sheets may have extended from the poles nearly to the equator, creating a snowball Earth that lasted for hundreds of millions of years. Yet this catastrophe also created new opportunities. Oxygen enables much more efficient metabolism than anaerobic processes. When organisms evolved ways to use oxygen for respiration, they could extract far more energy from food molecules than their anaerobic ancestors. This metabolic efficiency eventually made possible the evolution of larger, more complex organisms. However, this wouldn't happen immediately. After the initial rise, oxygen levels may have remained relatively low and unstable for over 1 billion years, a period sometimes called the boring billion, because relatively little seems to have happened in terms of evolutionary innovation. Around 600 million years ago, oxygen levels began rising again in what scientists call the Neoproterozoic oxygenation event. This second rise brought atmospheric oxygen to levels approaching or even exceeding those of today. Shortly afterward, in an evolutionary explosion of creativity, complex multicellular life appeared in the fossil record for the first time. The Cambrian period saw an astonishing diversification of life forms, with most of the major animal body plans we see today first appearing within a relatively brief span of perhaps 20 million years. The development of an ozone layer was another crucial consequence of atmospheric oxygen. Ozone, a molecule composed of 3 oxygen atoms instead of the usual 2, forms when ultraviolet radiation from the sun strikes oxygen molecules high in the atmosphere, splitting them into individual atoms that then recombine with other oxygen molecules. This ozone layer acts as a natural sunscreen for the planet, absorbing most of the harmful ultraviolet radiation before it can reach the surface. Before the ozone layer existed, UV radiation made the land surface inhospitable for life. Only in the oceans, where water provided shielding from UV rays, could life survive. The formation of the ozone layer eventually made it possible for life to colonize the land. Today, our atmosphere consists of roughly 78% nitrogen, 21% oxygen, and about 1% argon and other gases, including carbon dioxide. This composition has remained relatively stable for hundreds of millions of years, maintained by a complex interplay of geological and biological processes. Plants and photosynthetic algae continue to produce oxygen, while respiration by animals and microbes consumes it. Volcanic activity and weathering of rocks affect the balance of gases. The burial of organic carbon in sediments removes carbon from circulation while locking oxygen into the atmosphere. Why does oxygen remain at 21% rather than rising higher or falling lower? Scientists aren't entirely certain, but it seems that oxygen levels are regulated by feedback mechanisms. If oxygen were to rise much higher, perhaps to 30 or 35%, wildfires would become far more frequent and intense, consuming organic matter and releasing carbon dioxide while using up oxygen. If levels dropped too low, many organisms would suffer, potentially reducing the overall rate of photosynthesis until oxygen levels recovered. This delicate balance has persisted through numerous ice ages, warm periods, and mass extinctions, maintaining an atmosphere that has allowed life to flourish and diversify into millions of species. While humans have gazed up at the stars for millennia, we've only recently begun to explore the deepest recesses of our own planet. 7 miles beneath the surface of the Pacific Ocean lies the deepest known point on Earth's seafloor, the Challenger Deep in the Mariana Trench. This is a place of perpetual darkness, crushing pressure, and frigid temperatures. Yet even here, in what might seem like the most hostile environment imaginable, life has found a way to survive. The Mariana Trench stretches for more than 1,500 miles in a crescent shape east of the Mariana Islands in the Western Pacific. It averages about 43 miles wide, but it's the depth that makes it truly extraordinary. The Challenger Deep, located near the southern end of the trench, plunges down nearly 11,000 meters, or roughly 36,000 feet, below sea level. To put this in perspective, if you place Mount Everest, the tallest mountain on Earth, at the bottom of the Challenger Deep, its peak would still be more than a mile underwater. This immense depth results from the same tectonic processes that create mountains and earthquakes. The Mariana Trench marks a subduction zone, where the Pacific Plate, one of the largest tectonic plates on Earth, is diving beneath the smaller Mariana Plate. The Pacific Plate here is some of the oldest oceanic crust on the planet, up to 170 million years old. Because old oceanic crust is cold and dense, it sinks readily when it meets a younger, lighter plate, pulling the edge of the overriding plate downward and creating the deep trench we observe. The conditions at the bottom of the trench are extreme by any measure. The water temperature hovers just above freezing, between 1 and 4 degrees Celsius. But it's the pressure that truly defies imagination. At a depth of 11,000 meters, the water column above exerts a pressure of approximately 1,086 bar, or over 15,000 pounds per square inch. This is more than 1,000 times the atmospheric pressure we experience at sea level, equivalent to about 8 tons pressing down on every square inch. This pressure is so immense that it would instantly crush most human-made structures, and certainly any unprotected human body. Reaching such depths is an engineering challenge that makes space travel look straightforward. In space, you need to contain 1 atmosphere of pressure in a vacuum. In the deep ocean, you need to withstand thousands of atmospheres pressing in from all sides. Only a handful of vessels have ever successfully descended to the Challenger Deep. The first was the bathyscaphe Trieste, which carried Swiss oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh to a depth of 35,814 feet in 1960. They spent just 20 minutes on the bottom before beginning their ascent. But in that brief time, they made a crucial observation. Even at this incredible depth, they saw what appeared to be a flatfish swimming by their viewport. Life existed even here. For more than 50 years, no one returned to the deepest point on Earth. Then, in 2012, filmmaker James Cameron piloted the Deep Sea Challenger submersible to a depth of 35,756 feet, setting a record for the deepest solo dive. Cameron spent several hours on the bottom, collecting samples and filming the alien landscape. In 2019, explorer Victor Vescovo made the deepest dive on record, reaching 35,853 feet, and he made multiple dives to the trench over the following years, bringing various scientists along to study this extreme environment. What these explorers have found challenges our assumptions about where life can exist. The Hadal Zone, named after Hades, the Greek underworld, refers to ocean depths below 6,000 meters, and the Mariana Trench represents the deepest part of this zone. Despite the darkness, cold, and crushing pressure, the trench floor is not a lifeless wasteland. Mud samples from Challenger Deep have revealed approximately 200 different species of microorganisms, including types of plankton and bacteria specially adapted to these conditions. Larger organisms also thrive at these depths. Perhaps the most common large creatures are xenophyrophores, saucer-sized single-celled organisms that live on the sediment and feed by filtering it for organic matter. These remarkable organisms are among the largest single cells known to science, some reaching 4 inches across. Amphipods, which are somewhat like oversized shrimp, scavenge the trench floor in huge numbers, descending on any food that sinks down from above. Small sea cucumbers called holothurians also inhabit these depths, along with snailfish that hold the record for the deepest fish ever recorded, at depths approaching 8,200 meters. These deep-sea organisms have evolved remarkable adaptations to survive in their harsh environment. Their cell membranes contain special lipids that remain flexible under high pressure. Their proteins are structured differently from those of surface organisms, maintaining their function despite the crushing force. Many creatures in the trench are translucent, and their metabolism operates slowly, conserving energy in an environment where food is scarce. Any organic matter that sinks down from the sunlit surface waters above, whether dead plankton, fish, or even the occasional whale carcass, provides a vital source of nutrition for the trench ecosystem. The deepest living fish ever recorded, the Hadal snailfish, was found at depths approaching 8,200 meters in the Mariana Trench. This small, pink, scaleless creature has transparent skin so clear you can see through to its internal organs. Its body is about 96% water, making it barely denser than the surrounding seawater, and it lacks the gas-filled swim bladder that most fish use for buoyancy, as such an organ would be crushed at these depths. Instead, the snailfish has evolved a gelatinous, nearly boneless body that can withstand the pressure. Even stranger are the giant amphipods found in the Hadal zone, some reaching lengths of over 30 centimeters, more than 10 times the size of their shallow water relatives. These oversized crustaceans scavenge the seafloor, and experiments using baited cameras have shown them arriving at food sources in enormous numbers, quickly stripping flesh from any carcass that sinks into their domain. Their large size may be an adaptation to the sparse food supply, as a larger body can store more energy reserves to survive between the rare arrivals of food from above. Microbial life in the trench is equally fascinating. Scientists have discovered bacteria and archaea that thrive in the extreme conditions, some of which gain their energy not from sunlight or organic matter from above, but from chemical reactions with minerals in the rocks and sediments. These chemosynthetic organisms form the base of food webs, completely independent of the sun, similar to those found around hydrothermal vents elsewhere in the deep ocean. Some of these microbes can survive pressures even higher than those naturally occurring in the deepest trenches, suggesting that similar life might exist in the subsurface oceans of icy moons elsewhere in our solar system. The exploration of the Mariana Trench continues to reveal surprises. In 2020, scientists discovered a virus at a depth of 8,900 meters, the deepest virus ever found. This bacteriophage, a virus that infects bacteria, demonstrates that even the viral realm extends into the Hadal depths. The discovery has implications for understanding how viruses influence microbial populations in extreme environments, and how they might have evolved in Earth's early oceans. Hydrothermal vents have also been discovered in the Mariana Trench, though not at the deepest point. These underwater hot springs, where superheated water rich in minerals erupts from the sea floor, support rich ecosystems based on chemosynthesis rather than photosynthesis. Near these vents, scientists have found unique species of snails, mussels, crabs, and tube worms that exist nowhere else on Earth. Some of these organisms contain symbiotic bacteria in their tissues that convert the chemicals in the vent water into energy, sustaining their hosts in the darkness. The geology of the trench itself continues to be studied. As the Pacific Plate subducts beneath the Mariana Plate, it carries water-rich sediments and rocks down into the mantle. Eventually, heat and pressure drive this water out, causing it to rise into the overlying mantle wedge. This water lowers the melting point of the mantle rock, causing it to melt and form magma that rises to create the chain of volcanic islands known as the Mariana Islands, including Guam and other inhabited islands. The entire system, from trench to volcanic arc, represents one of Earth's most important tectonic factories, recycling oceanic crust back into the mantle and creating new continental-type crust through volcanic activity. Studying the Mariana Trench also helps scientists understand the mechanisms of earthquakes and tsunamis. Subduction zones like the Mariana Trench are capable of producing megathrust earthquakes, the largest and most destructive earthquakes on Earth. When the subducting plate sticks to the overlying plate and then suddenly slips, it can release enormous amounts of energy. While the Mariana Trench itself has not produced recent megathrust earthquakes, as devastating as those in other subduction zones like off Japan or Chile, understanding the processes here helps scientists prepare for such events elsewhere around the Pacific Ring of Fire. The discovery of life at such extreme depths has important implications for the search for life elsewhere in the universe. If organisms can thrive in the crushing pressure and darkness of the Hadal Zone, perhaps life could exist in the deep oceans thought to lie beneath the icy surfaces of moons like Europa or Enceladus, worlds that orbit Jupiter and Saturn respectively. The Hadal Zone proves that life doesn't need sunlight directly, just a source of chemical energy and organic molecules, requirements that might be met in many locations throughout our solar system and beyond. But the trench also reveals a sobering reality about human impact on the planet. Scientists have found plastic debris at the deepest points of the Mariana Trench, including a plastic bag at depths exceeding 10,800 meters. Microplastics have been found in the bodies of deep-sea creatures, and even at these remote depths, organisms show exposure to industrial pollutants that originated at the surface decades ago. It seems there is now no place on Earth, no matter how remote or extreme, that remains untouched by human activity. Earth's atmosphere is never truly still. Driven by uneven heating from the sun, the rotation of our planet, and the interactions between air, land, and ocean, our atmosphere generates weather phenomena ranging from gentle breezes to some of the most powerful forces nature can produce. Understanding these atmospheric dynamics has been crucial for human civilization, and it's becoming even more important as our climate continues to change. Hurricanes, typhoons, and cyclones, three names for essentially the same phenomenon depending on where they form, represent some of nature's most powerful storms. These massive rotating systems can span hundreds of miles and release energy equivalent to hundreds of nuclear bombs. They begin as areas of low pressure over warm ocean water, typically when sea surface temperatures exceed about 26 degrees Celsius or 80 degrees Fahrenheit. The warm water causes air to rise rapidly through evaporation and convection, creating an updraft. As this warm, moist air rises and cools, water vapor condenses into clouds and rain, releasing heat that powers the storm. The Coriolis effect, a consequence of Earth's rotation, causes the rising air to rotate. In the northern hemisphere, storms spin counterclockwise, while in the southern hemisphere, they spin clockwise. As the storm intensifies, more air rushes in toward the low-pressure center, accelerating as it spirals inward. Eventually, a calm eye forms at the storm's center, surrounded by the eye wall, where the strongest winds and heaviest rains occur. Hurricane wind speeds are classified on the Saffir-Simpson scale from Category 1, with winds of 74 to 95 miles per hour, up to Category 5, with sustained winds exceeding 157 miles per hour. But wind speed alone doesn't tell the full story of a hurricane's destructive potential. Storm surge, the rise in sea level caused by the storm's winds pushing water towards shore, has historically been responsible for most hurricane deaths in the United States. A major hurricane can raise water levels by 20 feet or more, flooding coastal areas and causing catastrophic damage. Heavy rainfall can drop more than a foot of rain in a day, causing inland flooding that can be just as devastating as the coastal impacts. And hurricanes commonly spawn tornadoes, adding another layer of danger. Recent research suggests that climate change is making the strongest hurricanes more intense. Warmer ocean temperatures provide more energy for storm development, and a warmer atmosphere can hold more moisture, leading to heavier rainfall. While scientists are still working to understand whether the total number of hurricanes will increase, there's growing evidence that the most intense storms, categories 4 and 5, are becoming more frequent in some regions. Additionally, some hurricanes now strengthen more rapidly than before, giving coastal communities less time to prepare and evacuate. Tornadoes, while generally much smaller than hurricanes, can produce winds even more intense than those in the strongest hurricanes. These violently rotating columns of air extend from severe thunderstorms to the ground, with wind speeds that can exceed 300 miles per hour in the most extreme cases. The United States experiences more tornadoes than any other country, with an average of about 1,200 per year, most occurring in spring and early summer, in an area of the Great Plains known as Tornado Alley. Tornadoes form when particular atmospheric conditions come together. Strong wind shear, meaning winds change speed and direction with altitude, combined with warm, moist air near the surface and cooler, drier air above. This creates instability, and when a trigger such as a cold front provides the initial lift, towering thunderstorms called supercells can develop. Inside these storms, the wind shear can create a rotating updraft called a mesocyclone. When this rotation extends downward and touches the ground, a tornado is born. The enhanced Fujita scale rates tornadoes from EF0 with winds of 65 to 85 miles per hour causing light damage, to EF5 with winds exceeding 200 miles per hour capable of completely destroying well-built homes and hurling cars hundreds of yards. The path a tornado takes can be narrow, sometimes just yards wide, or over 2 miles across, and can extend for dozens of miles or disappear within minutes. This unpredictability makes tornadoes particularly frightening and difficult to forecast precisely. Heat waves represent another form of extreme weather that's becoming more frequent and intense as global temperatures rise. A heat wave is typically defined as a period of abnormally hot weather, lasting days to weeks. While the specific temperature threshold varies by region based on what's typical for that area, heat waves can be deadly. High temperatures stress the human body, particularly when combined with high humidity that prevents cooling through perspiration. Vulnerable populations, including the elderly, very young, and those with chronic health conditions, are especially at risk. The physics behind heat waves usually involves persistent high-pressure systems that create a dome of hot air over a region, preventing cooler air from moving in and allowing temperatures to build day after day. Clear skies under these high-pressure domes allow strong sunlight to heat the ground intensely, which in turn heats the air above. When heat waves occur in cities, the urban heat island effect can intensify them further, as concrete and asphalt absorb and retain more heat than natural landscapes. Extreme precipitation events, whether heavy rain, intense snowfall, or severe flooding, are also becoming more common in many regions. The atmosphere's capacity to hold moisture increases by about 7% for every degree Celsius of warming, following fundamental physics known as the Clausius-Clapeyron relation. This means that when storms do form in a warmer atmosphere, they have access to more water vapor, potentially leading to heavier downpours and increased flood risk. Droughts represent the opposite extreme, periods of abnormally dry conditions that can persist for months or years. causing water shortages, crop failures, and increased wildfire risk. While droughts might seem like simply an absence of rain, they often result from complex interactions between oceanic patterns like El Niño and La Niña, atmospheric circulation changes, and local factors. In a warming climate, droughts can be intensified by higher evaporation rates that dry out soils more quickly, even if precipitation doesn't decrease. These extreme weather events don't occur in isolation. They're all part of Earth's complex climate system, influenced by factors including the jet streams that steer weather systems, ocean currents that transport heat around the globe, and numerous oscillations and patterns that shift over months or years. Understanding these connections and how they're changing as our planet warms is one of the great challenges facing climate science today. The weather may be unpredictable in detail, but the broad patterns and trends are becoming clearer, helping us prepare for the changes ahead. The year 2024 and the early months of 2025 have brought a cascade of new discoveries that are reshaping our understanding of the universe. From supermassive black holes to interstellar visitors, from the first moments after the Big Bang to potential signs of life on distant worlds, astronomical research continues to unveil cosmic wonders that would have seemed impossible just decades ago. One of the most exciting discoveries of 2024 was the identification of Gaia BH3, the most massive stellar mass black hole ever found in the Milky Way galaxy. Detected by the European Space Agency's Gaia spacecraft, which is precisely mapping the positions and motions of over 1 billion stars, this black hole was revealed through its gravitational effect on a companion star. The star orbits the black hole in a peculiar wobbling motion, and careful analysis of this movement indicated that the invisible companion must have a mass at least 33 times that of our Sun. This makes Gaia BH3 substantially more massive than the typical stellar black holes found in our galaxy, which usually contain between 5 and 20 solar masses. The discovery challenges our understanding of how massive stars evolve. When a star much more massive than the Sun exhausts its nuclear fuel, its core collapses catastrophically, potentially forming a black hole. But the details of this process, including how much mass ends up in the final black hole versus being ejected in the explosion, remain poorly understood. Gaia BH3's large mass suggests its progenitor star was probably exceptionally massive and may have contained relatively few elements heavier than hydrogen and helium, a composition more typical of the early universe. Finding such a massive black hole in our own galaxy, formed from a star rather than growing through mergers over time, helps astronomers understand the range of outcomes possible when giant stars die. Even more extreme are the ultramassive black holes lurking in the hearts of distant galaxies. In 2025, astronomers using the Very Large Telescope and Hubble Space Telescope discovered a dormant ultramassive black hole at the center of a galaxy called the Cosmic Horseshoe, 5 billion light-years away. This black hole contains approximately 30 billion times the mass of the Sun. To discover it, researchers exploited gravitational lensing, the bending of light from background objects by the gravity of massive foreground objects. The Cosmic Horseshoe Galaxy is so massive that it warps space-time significantly, bending light from even more distant galaxies behind it into a horseshoe-shaped pattern. By studying how this lensing affects the light, astronomers could measure the total mass in the cosmic horseshoe, including its central black hole. Among the most massive black holes ever observed is TON 6on18, a distant quasar whose central black hole has been estimated at anywhere from 40 to 66 billion solar masses, depending on the measurement technique used. These ultramassive black holes pose a significant puzzle. How did they grow so large? Even if a black hole formed in the early universe and steadily consumed surrounding material, there are physical limits to how fast it can grow, because infalling matter heats up and radiates energy, creating pressure that can push material away. Yet we observe supermassive black holes containing billions of solar masses that seem to have formed when the universe was less than 1 billion years old. Understanding how black holes could grow so massive so quickly is one of the key questions driving research today. The James Webb Space Telescope, humanity's most powerful space observatory, continues to revolutionize our view of the cosmos despite being operational for less than 3 years. Operating primarily in infrared wavelengths, Webb can peer through cosmic dust that blocks visible light and can see the light from the universe's first galaxies, which has been stretched into the infrared by the expansion of space during its long journey to Earth. Among Webb's remarkable achievements is the discovery of extremely distant galaxies that appear to have already assembled into surprisingly mature structures when the universe was just a few 100 million years old. One galaxy, observed as it appeared just 600 million years after the Big Bang, has a mass similar to what the Milky Way had at the same stage of development. Named the Firefly Sparkle because of its 10 bright star clusters, this galaxy is helping astronomers understand how the first galaxies assembled from clouds of gas in the young universe. Webb has also made significant contributions to exoplanet science, the study of planets orbiting other stars. In 2024, the telescope detected potential signs of biological activity in the atmosphere of K2-18b, a planet about 9 times Earth's mass orbiting a red dwarf star 120 light-years away. The planet appears to have a hydrogen-rich atmosphere with significant amounts of water vapor and possibly dimethyl sulfide, a compound on Earth primarily produced by marine phytoplankton. While these observations are still being debated and alternative explanations exist, they represent some of the most intriguing hints yet that we might be able to detect signs of life on worlds beyond our solar system. The telescope also captured the first ever 3-dimensional atmospheric map of an exoplanet. WASP-18b, a massive hot Jupiter orbiting extremely close to its star, revealed striking temperature contrasts across its atmosphere, with regions so hot they can destroy hydrogen molecules. These kinds of detailed atmospheric studies were impossible before Webb, and they're helping astronomers understand the incredible diversity of planetary atmospheres in the galaxy. Closer to home, our solar system received visitors from interstellar space. The comet 3I Atlas, also designated as Comet A2024-D1, passed through our solar system in 2024 and early 2025, providing scientists with a rare opportunity to study an object that formed around a distant star. Previous interstellar visitors include Oumuamua in 2017, whose unusual elongated shape and unexpected acceleration sparked debate about its nature, and Comet Borisov in 2019, which appeared more conventionally comet-like. Analysis of 3I Atlas revealed an unusually high carbon dioxide content and suggested the comet is extremely old, possibly dating back billions of years. Studying such objects gives astronomers a glimpse into the chemistry and conditions around other stars' planetary systems without having to travel there. NASA deployed multiple spacecraft to observe the comet, gathering data on its composition, structure, and how it interacted with our sun's radiation. Though 3I Atlas has now left our solar system forever, the information it provided will be analyzed for years to come. The universe continues to surprise us with phenomena we're only beginning to understand. In 2025, astronomers discovered a new moon orbiting Uranus, designated S2025 U1. this tiny. Moon, so small and faint that it escaped detection during Voyager 2's flyby nearly 40 years ago, was finally spotted by Webb's near-infrared camera. The discovery reminds us that even in our own solar system, there are still hidden worlds waiting to be found. Meanwhile, the Sun's mysteries are slowly being unraveled. The Parker Solar Probe, which in 2024 made the closest approach to the Sun of any spacecraft, flying within just 3.8 million miles of the solar surface, has returned unprecedented images and data. The probe's observations revealed the Sun's corona in extraordinary detail, showing coronal mass ejections and the solar wind's source regions with clarity never before achieved. Understanding the Sun's behavior is crucial not just for basic science, but for protecting our technology-dependent civilization from the effects of space weather. One of the year's most surprising discoveries came from long-term observation of Betelgeuse, the red supergiant star in Orion's shoulder. For years, astronomers have been puzzled by the star's unusual dimming patterns. In 2025, they confirmed that Betelgeuse has a companion star, a small star orbiting the supergiant that helps explain its brightening and dimming cycles. This Beetle Buddy, as it's affectionately called, adds to our understanding of how massive stars like Betelgeuse evolve and interact with stellar companions in the years before they explode as supernovae. Our Sun, that familiar ball of light in our sky, remains full of mysteries despite being the most studied star in the universe. It's a medium-sized star, classified as a G-type main-sequence yellow dwarf, with a surface temperature of about 5,500 degrees Celsius. But the Sun's visible surface, called the photosphere, is actually cooler than the atmosphere above it. The corona, the Sun's outer atmosphere visible during total solar eclipses as a shimmering halo of light, reaches temperatures exceeding 1 million degrees Celsius, a seeming impossibility that physicists have struggled to explain. The leading theory suggests that powerful magnetic fields threading through the Sun's atmosphere occasionally snap and reconnect, releasing bursts of energy that heat the corona. These magnetic processes also accelerate charged particles away from the Sun, creating the solar wind that streams through the solar system at speeds exceeding 400 kilometers per second. When this wind reaches Earth, it's deflected by our magnetic field, but some particles spiral down toward the poles where they collide with atmospheric molecules, creating the shimmering curtains of light we call auroras. The Sun isn't uniform or static. Its surface is covered with sunspots, dark regions that appear darker only because they're slightly cooler than their surroundings, though still at temperatures of several thousand degrees. These spots mark areas where strong magnetic fields poke through the surface, inhibiting convection and preventing hot material from reaching the surface. The number of sunspots varies over an approximately 11-year cycle, from solar minimum, when the Sun may have few or no spots, to solar maximum, when dozens might be visible at once. In 2024, solar physicists announced that the Sun had reached solar maximum, entering a period of heightened activity. During these active periods, the Sun experiences more frequent solar flares, sudden releases of magnetic energy that can send radiation and charged particles streaming toward Earth. Particularly powerful flares can disrupt radio communications, damage satellites, and even threaten astronauts in space. Coronal mass ejections, massive eruptions that hurl billions of tons of solar material into space, can trigger geomagnetic storms when they strike Earth's magnetic field. The Sun generates its energy deep in its core through nuclear fusion, where the intense pressure and temperature force hydrogen nuclei to fuse into helium, releasing tremendous energy in the process. But this energy doesn't travel directly from the core to the surface. Photons produced in the core bounce around randomly, absorbed and re-emitted countless times as they gradually work their way outward through the dense interior. This random walk is so slow that photons generated in the core today may not reach the surface for tens of thousands to millions of years. Only when they finally escape from the photosphere do they stream freely through space, traveling at the speed of light to reach Earth in just 8 minutes and 20 seconds. Our solar system's planets each have their own fascinating characteristics and ongoing mysteries. Mercury, the closest planet to the Sun, is a world of extremes, with dayside temperatures reaching 430 degrees Celsius, while nightside temperatures plunge to -180 degrees. Despite having essentially no atmosphere to trap heat, Mercury has ice in permanently shadowed craters at its poles, where the sun's rays never reach. Venus, Earth's evil twin as it's sometimes called, demonstrates how a planet of similar size and composition to Earth can evolve into a hellish hothouse. With an atmosphere 90 times thicker than Earth's and composed mostly of carbon dioxide, Venus experiences a runaway greenhouse effect that has raised surface temperatures to around 465 degrees Celsius, hot enough to melt lead. Sulfuric acid clouds shroud the planet, and the atmospheric pressure at the surface is equivalent to being almost a kilometer underwater on Earth. Yet Venus may once have been more Earth-like, with oceans and perhaps even life, before some event, possibly linked to volcanic activity, triggered the runaway greenhouse effect. Mars, the red planet, has long fascinated humanity as the most Earth-like of our neighboring worlds and the most promising place to search for past or present life. Recent research has revealed intriguing new findings. Using seismic data from NASA's InSight lander, which operated on Mars from 2018 to 2022, scientists have found evidence for a large underground reservoir of liquid water deep beneath the Martian surface, perhaps containing enough water to fill oceans on the surface if it could be extracted. This discovery is crucial because liquid water is essential for life as we know it. The gas giants, Jupiter and Saturn, continue to reveal their secrets through ongoing observations. The Hubble Space Telescope's Outer Planet Atmospheres Legacy program has monitored these worlds since 2014, tracking the evolution of their dynamic weather systems. Jupiter's Great Red Spot, a storm larger than Earth that has raged for at least 3 centuries, continues to shrink for reasons not fully understood. New storms form and dissipate, and the planet's cloud bands shift and change color as chemical reactions driven by sunlight and lightning alter the composition of the visible cloud layers. Saturn's rings, those stunning bands of ice and rock that make the planet instantly recognizable, are gradually disappearing. Material from the rings constantly rains down onto Saturn's upper atmosphere, pulled by gravity and pushed by micrometeoroid impacts. Cassini spacecraft observations suggested the rings could vanish within just 100 million years, a blink of an eye in planetary terms. This finding supports the idea that Saturn's rings are relatively young, perhaps formed from a shattered moon or captured comet within the last few 100 million years. The ice giants Uranus and Neptune, the most distant planets in our solar system, remain poorly explored. Only Voyager 2 has visited them, flying past Uranus in 1986 and Neptune in 1989. These encounters revealed worlds quite different from Jupiter and Saturn, with Uranus tipped on its side so that its axis of rotation lies almost in the plane of its orbit, perhaps due to an ancient collision, and Neptune displaying the fastest winds in the solar system at speeds exceeding 2,000 kilometers per hour. In October 2024, NASA launched the Europa Clipper spacecraft, on a mission to study Jupiter's moon Europa in detail. Europa is one of the most promising places to search for life beyond Earth. Beneath its icy crust lies a global ocean of liquid water, kept from freezing by tidal heating as Jupiter's gravity flexes the moon. Europa Clipper will fly by the moon nearly 50 times, using radar to probe beneath the ice, analyzing the composition of the surface, and looking for plumes of water vapor that might be erupting from the subsurface ocean. The spacecraft won't reach Jupiter until 2030, but when it does, it may revolutionize our understanding of where life can exist. Stars are the engines that drive the universe's evolution, forging the heavy elements that make up planets and people, illuminating the cosmos, and powering phenomena from gentle planetary systems to violent gamma-ray bursts. Understanding how stars are born, live, and die has been one of astronomy's great quests, and recent observations continue to refine our knowledge. The diversity of stars in our galaxy is staggering. The smallest stars, called red dwarfs, have masses as low as about 8% that of our Sun. These dim, cool stars burn their hydrogen fuel so slowly that they can live for trillions of years, far longer than the current age of the universe. None of the red dwarfs that formed in the early universe have yet died, and none will for countless eons to come. They glow with a dull red light, and though they're by far the most common type of star in the galaxy, making up perhaps 3/4 of all stars, they're so faint that not a single one is visible to the naked eye from Earth, despite our galaxy containing hundreds of billions of them. At the other extreme are the blue supergiants and hypergiants, stars with masses tens or even hundreds of times greater than the Sun. These stellar behemoths shine with incredible brilliance, some emitting as much light as 1,000,000 suns. But their profligate energy expenditure means they live fast and die young, exhausting their nuclear fuel in just a few million years. Rigel in the constellation. Orion is a blue supergiant about 20 times the Sun's mass and over 120,000 times more luminous. Its surface temperature exceeds 11,000 degrees Celsius, compared to the Sun's relatively cool 5,500 degrees. Between these extremes lie stars of every intermediate size and temperature. Orange dwarfs like Alpha Centauri b are slightly smaller and cooler than the Sun, but still capable of maintaining stable planetary systems for billions of years. White dwarfs like Procyon b have exhausted their nuclear fuel and collapsed to planet-sized remnants, but remain hot from their formation and slowly cooling over billions of years. Variable stars like Cepheids pulse in brightness with regular periods, expanding and contracting like beating hearts, their precise rhythms allowing astronomers to measure cosmic distances with remarkable accuracy. Brown dwarfs occupy a twilight zone between the largest gas giant planets and the smallest true stars. With masses between about 13 and 80 times that of Jupiter, brown dwarfs form like stars from collapsing gas clouds, but they never achieve the core temperatures and pressures necessary to sustain hydrogen fusion. They glow dimly from heat left over from their formation and from fusion of deuterium, a heavy form of hydrogen, which can occur at lower temperatures than normal hydrogen fusion. As they age, brown dwarfs gradually cool and fade, eventually becoming invisible in ordinary light, detectable only in the infrared. Stars form when dense regions in massive clouds of gas and dust, called molecular clouds, collapse under their own gravity. These clouds, often light years across and containing enough material to form hundreds of thousands or even millions of stars, are some of the coldest places in the galaxy, with temperatures just tens of degrees above absolute zero. When a region becomes dense enough, perhaps triggered by a passing shock wave from a nearby supernova or by the cloud colliding with another cloud, gravity begins pulling material inward. As the collapsing region contracts, it heats up and begins to spin faster, like a figure skater pulling in their arms. The spinning material flattens into a disk surrounding the growing protostar at the center. Magnetic fields thread through this disk, and complex interactions between the field, the disk, and the central star can launch jets of material perpendicular to the disk, blasting out into space at speeds of hundreds of kilometers per second. These jets, visible as glowing streams when they collide with surrounding gas, help the young star shed excess angular momentum that would otherwise prevent it from forming. Eventually, the protostar's core becomes hot and dense enough for nuclear fusion to begin, and a new star is born. The star's future is largely determined by its mass. Stars much less massive than the Sun will burn their hydrogen fuel slowly, shining dimly but lasting for trillions of years, far longer than the current age of the universe. Medium-sized stars like our Sun have lifetimes of about 10 billion years, spending most of that time steadily fusing hydrogen into helium in their cores. Massive stars, with 10 or more times the Sun's mass, burn their fuel ferociously and die young, lasting only a few million years before meeting explosive ends. When a Sun-like star exhausts the hydrogen in its core, fusion stops and the core contracts under its own weight, heating up in the process. This heat causes the star's outer layers to expand dramatically, creating a red giant star that can grow to hundreds of times its original size. Our Sun will eventually expand into a red giant in about 5 billion years, likely engulfing Mercury and Venus and possibly reaching Earth's orbit. During this phase, the star fuses helium into carbon and oxygen in its core, while hydrogen fusion continues in a shell around the core. For stars like the Sun, this is about as far as fusion can go. The core never gets hot enough to fuse carbon and oxygen into heavier elements. Instead, the star pulsates, ejecting its outer layers in successive pulses that form a glowing planetary nebula, a bubble of gas expanding into space and illuminated by ultraviolet light from the hot stellar core left behind. This core, called a white dwarf, is about the size of Earth, but contains roughly half the mass of the original star, making it incredibly dense. A teaspoon of white dwarf material would weigh tons. White dwarfs don't generate any energy through fusion. They simply shine by radiating away the heat left over from their formation. Over billions or trillions of years, they gradually cool and fade, eventually becoming black dwarfs, cold, dark cinders that no longer emit visible light. However, the universe isn't old enough yet for any white dwarfs to have cooled to this final state. Massive stars undergo a more dramatic fate. They progress through fusion stages rapidly, each one shorter than the last. After exhausting hydrogen, they fuse helium into carbon and oxygen. Then carbon and oxygen fuse into neon, magnesium, silicon, and other elements, all the way up to iron. But iron is a dead end. Fusing iron into heavier elements consumes energy rather than releasing it, so no further fusion can occur to support the star against gravity. When a massive star's core becomes mostly iron, catastrophe strikes. In a fraction of a second, the core collapses from perhaps the size of Earth to a sphere just 20 kilometers across, reaching densities so extreme that atomic nuclei are crushed together and electrons are forced to merge with protons, forming neutrons. The collapse releases a tremendous amount of gravitational energy, most of it carried away by neutrinos. but the infalling outer layers rebound off the collapsed core and are blasted back into space in a supernova explosion. For a few weeks, a supernova can outshine its entire host galaxy of billions of stars. The explosion scatters into space all the elements the star created during its lifetime, plus new elements forged in the extreme conditions of the explosion itself. Elements heavier than iron, including gold, platinum, uranium, and others, are primarily created in supernovae, and even more exotic events like neutron star collisions. Everything in your body except hydrogen was created in stars and supernova events, making you quite literally made of star stuff. In November 2025, astronomers captured something unprecedented. The moment a supernova broke through a star's surface. The nearby supernova, SN 2024 GGI, revealed a surprisingly olive-shaped blast, very different from the spherical explosions typically assumed. This observation is helping astronomers understand the complex physics of stellar explosions and how asymmetries in the collapsing star can shape the resulting supernova. What remains after a supernova depends on the original star's mass. If the core's mass is below a certain limit, about 3 times the mass of the Sun, it remains as a neutron star. These objects are the densest stable matter in the universe. A neutron star packs more mass than the Sun into a sphere the size of a city, with densities so extreme that a sugar cube-sized piece would weigh 1 billion tons. Neutron stars can spin incredibly fast, hundreds of times per second, powered by the conservation of angular momentum as the star's core collapsed. Many emit beams of radiation from their magnetic poles, and if these beams sweep across Earth, we detect regular pulses, earning these objects the name pulsars. If the collapsed core exceeds about 3 solar masses, nothing can prevent its further collapse. Gravity overwhelms all resistance, and the core collapses to infinite density, creating a black hole. Not even light can escape from within the event horizon, the boundary surrounding the black hole, giving these objects their name. We know black holes exist because we can observe their gravitational effects on nearby matter and detect the radiation emitted by material falling toward them. In 1915, Albert Einstein's general theory of relativity predicted that accelerating massive objects would create ripples in the fabric of space-time itself, traveling outward at the speed of light like waves on a pond. These gravitational waves carry energy away from the accelerating masses, but Einstein himself doubted they would ever be detected because the effect is so incredibly tiny. Even the most violent cosmic events produce gravitational waves that stretch and compress space by less than 1 part in 10 billion billion when they reach Earth, a displacement smaller than the diameter of an atomic nucleus spread across kilometers. For a century, gravitational waves remained purely theoretical. Then, on September 14, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, one in Washington State and one in Louisiana, simultaneously detected a signal lasting less than 1/4 of a second. The signal matched precisely what theory predicted for 2 black holes, with masses about 30 times that of the Sun each, spiraling together and merging into a single larger black hole over 1 billion light-years away. This detection, announced publicly in February 2016, opened an entirely new way of observing the universe. Gravitational wave detectors work on the principle of interferometry. LIGO's detectors consist of 2 perpendicular tunnels, each 4 kilometers long, with laser light bouncing back and forth between mirrors at each end. When a gravitational wave passes through, it temporarily stretches space in one direction while compressing it perpendicular to that direction. This causes one arm of the detector to become slightly longer, while the other becomes slightly shorter, changing the time it takes light to travel each path. When the light beams are recombined, they interfere with each other, creating a pattern that reveals the passing wave. The change in arm length that LIGO can detect is astoundingly small, about 1/10,000th the width of a proton, yet the detectors routinely achieve this sensitivity. Since that first detection, LIGO and its international partners, including Virgo in Italy and Kaga in Japan, have detected dozens of gravitational wave events. Most come from merging black holes, but others have come from neutron-star collisions. On August 17, 2017, detectors caught gravitational waves from two neutron stars spiraling together. This event, designated GW170817, was particularly significant because it was also detected electromagnetically, telescopes around the world quickly swiveling to observe the source in gamma rays, X-rays, optical light, and radio waves. The neutron-star merger produced a kilonova, an explosion powered by the radioactive decay of heavy elements created in the collision. Observations of this kilonova confirmed that neutron-star mergers are indeed one of the primary factories where elements heavier than iron are forged. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. All these elements were primarily created in such violent collisions, then scattered into space to eventually become incorporated into new generations of stars, planets, and ultimately into us. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of black holes, neutron stars, and extreme physics. We've discovered that black holes come in a wider range of masses than previously thought, including some in a middle range that was theoretically unexpected. We've measured how often these mergers occur, helping us understand how often the universe experiences these most violent events. We've tested Einstein's theory of general relativity under conditions far more extreme than any laboratory could reproduce, and so far, the theory passes every test with flying colors. Future gravitational wave observatories will be even more sensitive and able to detect a wider range of sources. The space-based LISA mission, planned for launch in the 2030s, will have 3 spacecraft forming a triangular detector millions of kilometers across, able to detect lower frequency gravitational waves from supermassive black hole mergers and other sources invisible to Earth-based detectors. Ground-based detectors like Einstein Telescope in Europe and Cosmic Explorer in the United States will push sensitivity to new extremes, potentially able to detect every black hole and neutron star merger in the observable universe. The detection of gravitational waves has also sparked new possibilities for understanding the universe's earliest moments. Some theories predict that the universe's inflation phase shortly after the Big Bang would have produced a background of gravitational waves, much as the hot early universe produced the cosmic microwave background of light. Detecting this primordial gravitational wave background would provide unprecedented insight into the physics of the very early universe, testing theories about how the cosmos began and how fundamental forces behaved when the universe was a fraction of a second old. Gravitational waves have even entered the realm of pulsar timing arrays. By precisely monitoring the arrival times of pulses from distant pulsars, astronomers can detect the passage of very low-frequency gravitational waves with periods of years or decades. These waves likely come from supermassive black hole binaries, pairs of black holes containing millions or billions of solar masses each, slowly spiraling together at the centers of merged galaxies. In 2023, multiple pulsar timing array projects around the world announced the detection of a background hum of these gravitational waves, like listening to the combined sound of many orchestras playing simultaneously far away. This background represents the collective effect of countless supermassive black hole mergers occurring throughout the universe over billions of years. Perhaps the most profound realization in modern cosmology is that everything we can see, all the stars, galaxies, and glowing gas that astronomy has traditionally studied, represents only about 5% of the total content of the universe. The remaining 95% is something else entirely, matter and energy that don't emit or absorb light, but whose effects dominate the large-scale structure and fate of the cosmos. Dark matter comprises about 27% of the universe's total content. We infer its existence from its gravitational effects. When astronomers measure how fast stars orbit in galaxies, they find that stars in the outer regions move much faster than they should, if only the visible matter in the galaxy provided the gravitational force. Either our understanding of gravity is wrong on galactic scales, or there's a lot more matter present than we can see. Similar evidence comes from galaxy clusters, where the motion of galaxies and the behavior of hot gas indicate far more mass than visible matter can account for. Perhaps the most compelling evidence comes from gravitational lensing. As Einstein predicted, massive objects bend space and therefore bend the path of light passing near them. When light from distant galaxies passes through or near a massive cluster of galaxies, the cluster's gravity acts like a lens, bending and distorting the background galaxy's images. By studying these distortions, astronomers can map how mass is distributed in the cluster. The results consistently show halos of invisible matter extending far beyond the visible galaxies, with far more mass in these halos than in all the visible matter combined. Despite intensive searches, we don't know what dark matter actually is. It's not ordinary matter made of protons, neutrons, and electrons, because such matter would interact with light at least occasionally. The leading candidates are exotic particles predicted by various extensions to the standard model of particle physics, but not yet discovered. Based on theoretical models, these particles could range from lightweight axions to heavier weakly interacting massive particles, or WIMPs. Direct detection experiments around the world are trying to catch dark matter particles as they pass through Earth, while particle accelerators like the Large Hadron Collider search for evidence of these particles in high-energy collisions. So far, dark matter remains frustratingly elusive. Even more mysterious is dark energy, which comprises about 68% of the universe's total content. Dark energy was discovered through observations of distant supernovae in the late 1990s. Astronomers were attempting to measure how the universe's expansion is slowing down over time due to gravity pulling everything back together. To their surprise, they found the opposite. The expansion is accelerating. Something with repulsive gravitational properties, which physicists call dark energy, appears to be pushing space apart. The nature of dark energy is one of the deepest mysteries in physics. One possibility is that it represents the energy of empty space itself, a property called vacuum energy that quantum field theory suggests should exist, though the predicted value is vastly larger than observed. Another interpretation suggests it could be evidence of a new fundamental force or a modification to gravity on cosmic scales. Some theories propose it might be a dynamic field that changes over time, rather than a constant property of space. The true nature of dark energy remains unknown, and determining what it actually is represents one of the foremost challenges in modern cosmology. Dark energy's effects are subtle on small scales, but dominate on the largest scales. It's causing distant galaxies to accelerate away from us, and in the far future, this acceleration will become so extreme that galaxies outside our local group will recede faster than light can travel, disappearing beyond our cosmic horizon. Eventually, in perhaps 100 billion years, observers in the Milky Way would see a much lonelier universe, with only the handful of gravitationally bound galaxies in our local group visible, surrounded by emptiness as dark energy stretches the rest of the universe beyond view. Understanding dark matter and dark energy isn't just an academic exercise. These mysterious components dominate the universe's evolution, determining how structures form, how galaxies evolve, and what the ultimate fate of the cosmos will be. Whether the universe will expand forever, growing ever colder and more diffuse, or whether dark energy might change its properties, potentially leading to entirely different endings, depends on the nature of this dark sector that we're only beginning to study. Recent observations are helping constrain the properties of dark matter and dark energy. Studies of cosmic microwave background radiation, the afterglow of the Big Bang, combined with surveys mapping millions of galaxies, are refining measurements of dark energy's strength and how it changes over time, if at all. Searches for dark matter continue with increasing sensitivity. While we don't have definitive answers yet, the data are narrowing the possibilities, and there's hope that within the coming decades, we'll finally understand what most of the universe is made of. 14 billion years ago, give or take a few 100 million years, everything in our observable universe was compressed into a volume smaller than an atom. We can't say what happened before that moment, or even if before is a meaningful concept, because space and time themselves began with what we call the Big Bang. This wasn't an explosion in space, but rather an explosion of space, with the universe expanding and cooling from an initial state of extreme density and temperature. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from subatomic to astronomical scales in less time than it takes light to cross an atom. This rapid inflation smoothed out irregularities and stretched the universe to flatness, explaining why the cosmos appears so uniform when we look in different directions. Inflation also created tiny quantum fluctuations that were stretched to cosmic scales, seeding the density variations that would later grow into galaxies and clusters. As the universe expanded and cooled, fundamental forces that were initially unified separated into the distinct forces we observe today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Exotic particles created in the extreme early conditions quickly decayed into more familiar particles, like quarks and electrons. When the universe was about 1 microsecond old, quarks combined to form protons and neutrons. After a few minutes, these could fuse to form the first atomic nuclei, mostly hydrogen and helium, with traces of lithium and beryllium. But for the next 380,000 years, the universe remained opaque, a hot fog of electrically charged particles and photons constantly interacting. Light couldn't travel far before being scattered, much as fog scatters light on Earth. Then, as the universe cooled below about 3,000 degrees, electrons combined with atomic nuclei to form neutral atoms in an event called recombination. Suddenly, light could travel freely through space. The photons released at that moment have been traveling ever since, stretched by the universe's expansion from visible light into microwaves. We detect this cosmic microwave background radiation coming from all directions in the sky, a snapshot of the universe at age 380,000 years. The cosmic microwave background is remarkably uniform, with temperature variations of only 1 part in 100,000. But those tiny variations are crucial. Slightly denser regions in the early universe had slightly stronger gravity, attracting more matter and growing denser still. Over hundreds of millions of years, these density fluctuations grew, with matter collapsing into the first stars and galaxies while leaving vast voids between them. The pattern of galaxies we see today, with clusters connected by filaments and separated by enormous empty regions, grew from those primordial fluctuations imprinted in the cosmic microwave background. The first stars, formed perhaps 100 to 200 million years after the Big Bang, were very different from stars today. They formed from pure hydrogen and helium, with no heavier elements because those hadn't been created yet. Computer simulations suggest these first stars were probably very massive, hundreds of times the mass of the Sun, burning through their fuel in just a few million years before exploding as supernovae and creating the first heavy elements. However, since we cannot directly observe these ancient stars, our understanding comes from theoretical models and indirect evidence. The light from these first stars, based on what models predict, ionized the surrounding hydrogen, creating bubbles of clear space that gradually merged, ending the cosmic dark ages and beginning the era of rionization. The James Webb Space Telescope is now observing galaxies from this epoch, seeing them as they appeared when the universe was less than 1 billion years old. These observations are challenging our understanding of how quickly galaxies could form and evolve. Some early galaxies appear surprisingly mature, with already formed spiral structures or large stellar populations, suggesting that galaxy formation may have been more efficient in the early universe than current models predict. As time passed, galaxies continued to grow through mergers and by accreting gas from their surroundings. Supermassive black holes formed at galaxy centers, though we still don't fully understand how they grew so quickly to billions of solar masses within the first billion years of cosmic history. The universe gradually evolved into the structure we see today, with hundreds of billions of galaxies, each containing billions to trillions of stars, organized into a cosmic web of clusters, filaments, sheets, and voids. Our observable universe has a radius of about 46 billion light-years, much larger than the universe's age of 14 billion years might suggest. This is because space itself has been expanding while light travels toward us, meaning we can see objects that are now much farther away than they were when they emitted the light we're receiving. But this observable universe represents only the portion of the cosmos we can possibly see. Beyond this cosmic horizon lie regions that are receding from us faster than light can travel, regions we can never observe no matter how long we wait. The actual extent of the universe beyond our observable portion is unknown and perhaps unknowable. Current measurements suggest space is very close to flat on large scales, which, according to cosmological models, would be consistent with an infinite universe extending forever, with galaxies and stars we'll never see. However, the uncertainty in these measurements is still large enough that we can't rule out other possibilities, such as a finite but unbounded universe that wraps back on itself in higher dimensions, similar to how the surface of a sphere is finite but has no edge. One intriguing consequence of an infinite universe is a thought experiment about repetition. In an infinite universe with infinite matter, if you traveled far enough, you might theoretically encounter regions with identical arrangements of matter to our own, not because of any special connection, but simply because there are only so many ways matter and energy can be arranged. With infinite space and infinite possibilities being realized somewhere, every possible configuration would occur an infinite number of times. However, this remains a purely theoretical consideration based on mathematical extrapolations rather than observational evidence, and it leads to mind-bending philosophical questions about identity and uniqueness that physics alone cannot answer. Earth doesn't orbit the Sun in isolation. we share our path through space with countless chunks of rock and metal, remnants from the solar system's formation 4.5 billion years ago. Most of these objects reside in the asteroid belt between Mars and Jupiter, a ring of debris that never coalesced into a planet due to Jupiter's powerful gravitational influence. But some asteroids follow orbits that bring them close to Earth. And throughout our planet's history, these encounters have sometimes resulted in spectacular collisions that have shaped the course of life on our world. The asteroid belt contains millions of objects, ranging from tiny pebbles to Ceres, the largest member, which is nearly 1,000 kilometers in diameter and classified as a dwarf planet. These asteroids represent pristine samples of the solar system's early days, preserving material that has changed little since the planets formed. They're composed primarily of rock and metal, with compositions ranging from carbonaceous asteroids rich in water and organic compounds to metallic asteroids that may be the exposed cores of shattered protoplanets, and stony asteroids that resemble Earth's mantle rock. Some asteroids have been found to have their own moons. The binary asteroid Didymos and its companion Dimorphos became famous in 2022 when NASA's DART spacecraft deliberately crashed into Dimorphos in the first test of a planetary defense technique. The impact successfully altered Dimorphos's orbit around Didymos by several minutes, demonstrating that we could potentially deflect a dangerous asteroid if we detected it far enough in advance. This mission marked a milestone, humanity's first attempt to deliberately change the motion of a celestial body. While asteroids mostly remain safely distant, some follow paths that intersect Earth's orbit. These near-Earth objects, or NEOs, are carefully tracked by astronomers around the world. As of 2025, we've catalogued over 30,000 near-Earth asteroids, and we discover new ones almost daily. The vast majority pose no threat, passing by at safe distances or being too small to survive passage through Earth's atmosphere. But rare larger objects could potentially cause significant damage if they struck Earth. So understanding the population and improving our ability to predict future impacts is a high priority for planetary defense. Every day, Earth collects approximately 100 tons of material from space, mostly in the form of tiny particles called micrometeorites. These dust-sized grains, often remnants of comets or asteroids, burn up high in the atmosphere, creating the meteors or shooting stars we see streaking across the night sky. Most are completely vaporized, but some survive to reach the ground as meteorites. These space rocks provide valuable scientific information, as they're samples of other worlds delivered to our doorstep free of charge. Several times a year, Earth passes through streams of debris left behind by comets, producing meteor showers. As a comet orbits the Sun, solar heating causes ice to vaporize, releasing dust and small rocks that spread out along the comet's orbit. When Earth crosses these debris streams, we see increased numbers of meteors all appearing to radiate from a particular point in the sky, giving each shower its name. The Perseids in August, the Geminids in December, and the Leonids in November are among the most reliable annual meteor showers, each capable of producing dozens or even hundreds of visible meteors per hour under dark skies. Larger objects can survive atmospheric entry to reach the ground. The Chelyabinsk meteor, which exploded over Russia in 2013, was about 20 meters in diameter and released energy equivalent to about 500 kilotons of TNT, more than 20 times the yield of the atomic bomb dropped on Hiroshima. The blast wave damaged buildings and injured over 1,500 people, mostly from flying glass, as windows shattered across the region. Yet this object had gone completely undetected before its arrival, approaching Earth from the direction of the Sun, where telescopes couldn't see it. The event highlighted the need for better detection systems and the unpredictability of smaller impacts. Much larger impacts have occurred throughout Earth's history, with profound consequences. The most famous is the Chicxulub impact 66 million years ago, which contributed to or caused the extinction of the dinosaurs, along with about 3/4 of all plant and animal species. The impactor, estimated to have been about 10 to 15 kilometers in diameter, struck what is now the Yucatan Peninsula in Mexico with the force of billions of nuclear bombs. The impact vaporized rock, created a crater nearly 200 kilometers across, and ejected vast amounts of material into the atmosphere, blocking sunlight and causing global climate disruption that lasted for years or decades. But Chicxulub was far from the largest impact in Earth's history. Evidence from ancient rocks suggests even larger collisions occurred earlier, when the solar system was younger and impacts more frequent. During the late heavy bombardment, a period roughly 4 billion years ago, Earth and the other inner planets experienced an intense spike in impact rates, possibly caused by orbital changes in Jupiter and Saturn that destabilized the asteroid belt and Kuiper belt. Some impacts during this period may have been large enough to vaporize the oceans temporarily and sterilize Earth's surface, though life somehow persisted, perhaps in deep-sea hydrothermal vents or in subsurface environments. Scientists now recognize that impacts have played a crucial role in shaping life on Earth. While large impacts are destructive, causing mass extinctions and climate catastrophes, they also create opportunities. After the dinosaurs were wiped out by the Chicxulub impact, mammals, which had remained small and relatively insignificant for over 100 million years, rapidly diversified and grew larger, eventually giving rise to all modern mammal groups, including our own primate ancestors. Without that impact, intelligent life on Earth might never have evolved, or might have taken a completely different form. Smaller impacts continue today. In 2013, a newly discovered impact crater in China, measuring 900 meters across, was found to have formed during the Holocene, the current geological epoch. The Guangdong crater dwarfs other known recent impact sites and demonstrates that significant impacts can occur even in recent geological time. Meanwhile, monitoring programs watch the skies for future threats. NASA's Planetary Defense Coordination Office tracks potentially hazardous asteroids and develops strategies for dealing with them, including the kinetic impactor technique demonstrated by DART and alternative methods like gravity tractors that would use a spacecraft's gravitational pull to slowly alter an asteroid's orbit. The study of impact craters also provides insights into planetary history across the solar system. Mercury, the Moon, and Mars all bear heavily cratered surfaces, recording billions of years of impacts. In contrast, Earth's active geology has erased most ancient craters through erosion and plate tectonics. Of the roughly 190 confirmed impact craters on Earth, most are relatively recent in geological terms. Studying craters on other worlds, where they're better preserved, helps scientists understand impact rates over time and the evolution of the solar system. Meteorites themselves are treasures for scientists. Carbonaceous chondrites, primitive meteorites rich in carbon compounds, contain amino acids and other organic molecules, demonstrating that the building blocks of life can form in space and be delivered to planets. Martian meteorites, chunks of Mars blasted into space by asteroid impacts and later falling to Earth, provide samples of the red planet without the expense of a sample return mission. Iron meteorites, composed almost entirely of iron and nickel, are thought to be fragments of differentiated asteroids' cores, giving us direct samples of what lies deep inside rocky planets like Earth. One of the most profound questions humanity can ask is, are we alone? For most of history, this question could only be pondered philosophically or theologically. Today, we're finally developing the tools to search for answers through observation and experiment. The search begins with understanding what makes Earth habitable. Our planet orbits at just the right distance from the Sun for water to exist as a liquid on the surface, in what astronomers call the habitable zone, or sometimes the Goldilocks zone. Too close to the star, and water boils away. Too far, and it freezes solid. But being in the habitable zone isn't sufficient. Venus is technically in our Sun's habitable zone, but it's obviously not habitable. Earth has numerous other favorable characteristics. A large moon that stabilizes its axial tilt, keeping climate relatively steady, a magnetic field that shields us from radiation, plate tectonics that recycle materials and help regulate atmospheric composition, and a protective ozone layer. The combination of all these factors working together over billions of years has made Earth an oasis for life. As of now, we know of over 5,000 confirmed exoplanets, worlds orbiting other stars, with thousands more candidates awaiting confirmation. These discoveries have revealed an astonishing diversity of planetary systems. We've found hot Jupiters, massive gas giants orbiting so close to their stars that their atmospheres are being stripped away. We've discovered super-Earths, rocky planets several times our world's mass, with no equivalent in our solar system. Some planets orbit binary star systems, giving them two suns in their sky. Others drift through space as rogue planets, ejected from their birth systems and wandering the galaxy alone. Many exoplanets have been found in their stars' habitable zones, and some are potentially rocky worlds rather than gas giants. These include planets like TRAPPIST-1e, F, and G, three Earth-sized worlds orbiting a cool red dwarf star 40 light-years away, all potentially able to support liquid water. Proxima Centauri b orbits the nearest star to our Sun at a distance where temperatures might allow liquid water, though the intense radiation from its red dwarf host star raises questions about habitability. Dozens of other candidates are being studied, each representing a potential abode for life. But finding potentially habitable worlds is just the first step. We need to study their atmospheres to look for signs that life might actually be present. This is challenging because planets are vastly fainter than their stars and usually lost in the stellar glare. However, astronomers have developed several techniques. When a planet transits in front of its star from our perspective, blocking a tiny fraction of the star's light, some of that light passes through the planet's atmosphere. Different molecules absorb light at specific wavelengths, imprinting a chemical signature that we can detect. This technique, called transmission spectroscopy, is revealing the atmospheric composition of numerous exoplanets. The James Webb Space Telescope is revolutionizing this field. Its large mirror and sensitive infrared instruments can detect molecules in exoplanet atmospheres with unprecedented detail. In 2024, Webb studied K2-18b and potentially detected dimethyl sulfide, a molecule that on Earth is primarily produced by marine life. This detection is controversial and needs confirmation, but if verified, it could be one of the first detections of a biosignature, a chemical or combination of chemicals that might indicate biological activity. Scientists are also considering biosignatures beyond what we're familiar with on Earth. While oxygen in an atmosphere along with methane might indicate life, alien biochemistries might produce different combinations of gases. The search for technosignatures, indicators of technological civilizations like radio transmissions or atmospheric pollution from industry, represents another approach. Projects like Breakthrough Listen are surveying millions of stars for any sign of artificial signals. Closer to home, we're discovering that our solar system has multiple worlds that might harbor life. Mars likely once had liquid water flowing on its surface, with evidence of ancient river valleys, lake beds, and possibly an ocean covering much of the northern hemisphere. While the surface is now cold and dry, underground water may persist, and ancient microbial life might have evolved during Mars's wetter past. If such life existed, fossils, or even living microbes, could potentially be preserved in the subsurface, though this remains unconfirmed. Jupiter's moon, Europa, and Saturn's moon Enceladus both appear to have global oceans of liquid water beneath their icy shells, kept liquid by tidal heating as their host planet's gravity flexes them. Plumes of water vapor erupting from Enceladus have been sampled by the Cassini spacecraft, revealing complex organic molecules and evidence that the ocean interacts with rocky seafloor. This suggests the possibility of hydrothermal vents, similar to those on Earth's ocean floor, where ecosystems thrive without sunlight. Whether life actually exists in these hidden oceans remains unknown, but the conditions could be suitable. Europa Clipper will study Europa in detail to determine if its ocean might be habitable and to search for evidence that could indicate biological activity. Even more exotic are possibilities like Titan, Saturn's largest moon, which has lakes and seas of liquid methane and ethane on its surface rather than water. While Titan is far too cold for water-based life, some scientists speculate that alternative biochemistries based on liquid hydrocarbons might theoretically be possible, though this remains highly speculative and unproven. The Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in the mid-2030s, will deploy a drone to explore multiple locations on Titan's surface, searching for evidence of whether life, or at least complex organic chemistry that could be precursors to life, might exist in this strange world. The discovery of extremophiles on Earth, organisms that thrive in conditions once thought impossible for life, has expanded our ideas about habitability. Microbes have been found living in boiling hot springs, in the crushing pressure of the deep ocean, in acid mine drainage, and even in the dry valleys of Antarctica, where conditions approach those on Mars. Life has colonized nearly every niche on Earth where liquid water exists, however briefly. This resilience suggests that if life can emerge at all, it might be more common in the universe than once thought. Whether life exists elsewhere remains an open question. We might be the only living things in an entire galaxy of 400 billion stars, or life might be common, but intelligence rare, or technological civilizations might exist, but be too far away for us to detect them. Or perhaps we're on the verge of finding signs of life on worlds we can already see, waiting in data we've already collected. The search continues, driven by the profound implications any answer would have for our place in the universe. We've journeyed tonight from the crushing depths of the Mariana Trench to galaxies at the edge of the observable universe. We've witnessed how ancient microbes transformed Earth's atmosphere, making possible the evolution of complex life. We've explored the forces that shape our planet, from the slow dance of continents across the globe to the fury of hurricanes and tornadoes. We've marveled at discoveries of massive black holes, distant galaxies forming in the young universe, and potential signs of life on worlds orbiting other stars. The cosmos is vast, almost beyond comprehension, with hundreds of billions of galaxies, each containing billions or trillions of stars. Most of those stars likely accompanied by planets. Yet in all this vastness, As far as we yet know, Earth stands alone as a world teeming with life. Whether that will always be true remains to be seen, but it makes our small world precious, a blue oasis floating in the darkness, the only home we've ever known. The scientific journey continues. New telescopes are being built, new missions are being planned, new instruments are being developed that will probe deeper into space and further back in time. Questions that seem unanswerable today may yield to tomorrow's observations. The universe has surprised us repeatedly, revealing wonders we never imagined. There's no reason to think those surprises will stop. If you've enjoyed this journey through space and Earth tonight, we'd appreciate your support through likes and subscriptions. Your engagement helps us continue creating these explorations of science and discovery. Please feel free to share your thoughts in the comments below. What discoveries amazed you most? What questions do you still have? But for now, whether you're drifting off to sleep or simply enjoying a moment of quiet reflection, rest easy, knowing that you're part of this magnificent universe made of star stuff, standing on a planet that itself is remarkable, gazing up at mysteries that inspire wonder in every generation. Good night, and may your dreams be filled with stars.